Thanks for the introduction. I'm happy to be here to talk about the work on implementing finite element models for fluid structure interaction using neural networks. So essentially, I'm implementing these methods using a machine learning package so that we can get all the good properties of the machine learning package and what functionalities it provides with us. Right, so first, some introduction on fluid structure interaction. It certainly is very common in many engineering applications. So I'm giving two examples here. The first one is in a nuclear reactor where the coolant flow can interact with the fuel assembly, causing vibration or the rupture of the fuel cladding. The second example is flowing aorta, where the blood flow interacts with the blood vessel. And usually we want to use numerical methods or models to simulate such flow. And as a computational physicist, we always want to develop methods that has better accuracy and more efficient. Means it is scalable, that when you have a larger problem, many degree of freedoms, you still get the solution at a good speed. Use the hardware to the most. And conventionally, this model development is usually done on the CPU platform, but we have seen a lot of new hardware and softwares developing over the years. And largely, this development is driven by machine learning applications. So I'm listing some hardware in the box here. So we have conventionally CPU, but GPU is largely driven by machine learning. And there are even some dedicated AI accelerators for machine learning applications. They have larger cache and on-chip memories, a lot of parallel chips. And for programming models, we have the conventional MPI and OpenMP models. And also for these new hardwares, we have proprietary programming models for the parallel hardware, such as CUDA, Poplar, and HIP. They are by different manufacturers. And what we are doing here is that we will use neural network to represent the conventional numerical methods so that you can implement it with the machine learning package. And those packages give us access to those hardware so that once you have your models written in a way, it can automatically run on all those hardwares that's fastly developing and emerging. So in plain words, we are writing a finite element solvers using PyTorch. So besides the benefits I mentioned before, they leverage different software and hardware for machine learning. This method also have other benefits. So I want to mention the first one is it has easy integration with machine learning models. So if you have data-driven models for any part of your model, like parameterization for turbulence, that is trained from a neural network, it will be more easy to integrate those models with this architecture, with these finite element models implemented with neural networks. The second benefit I want to mention here is the automatic differentiation that is inherited in neural networks. So if you are writing any operations in PyTorch, you will get the gradient automatically. Like you just need to call back propagation, then it will give you the gradient of your output to the input. This will be very helpful if you are doing inverse problem or you're doing data simulation in many, like in atmospheric flow, when you try to simulate observation for weather prediction, for example. And how we're going to do that, I'm listing some options or some choices we made when developing the methods. So other colleagues in my group have developed the method for structure mesh. So it's essentially like a finite difference method. Then you will have a fixed filter that's like the convolutional filter that you use in image processing. But here I'm presenting the world for unstructured mesh so that you have a better geometric flexibility. And second choice I made is whether I'm going to use an explicit solver or an implicit solver. I'm using implicit solver here, although it doesn't have to be in that way if you're solving a compressible flow. But I'm dealing with incompressible flow, so you have the pressure field that is coupled over the whole domain, so you have to use implicit solver in some part of your equation. So for low order or high order method, I'm selecting high order method. So one reason is that you get higher accuracy, but the main reason higher is that for those massive parallel hardware, you usually want your computational cost, like the arithmetic computations at each time step or each memory retrieve, to be as much as possible to use your computation power to the most. So we are selecting high order method here. And the last choice I make here is whether to use a continuous or discontinuous Galerkin method. I'm using discontinuous method for its better parallel properties. We'll go over this in the next slides a little bit. We will see why it is like that. Yeah. To show you how I developed this method, I'm going to use the diffusion equation as an example. So it's an elliptic equation operation. So we will develop a multigrid method to inverse that discretized system. And once we get that multigrid method, we can apply that multigrid method as a preconditioner for our fluid structure and fluid structure interaction system. Yeah. So I'm putting the problem formulation for the diffusion equation here. I'm sure everybody's familiar with this. So it's like you can think it as a heat conduction problem. Yeah. So the discontinuous Galerkin method works as shown in this illustration here. So on the left is a Hessian domain that we want to solve our problems on in this illustration, and we do a triangulation, use 6 triangles to discretize the domain, and then for each of the triangle we have a subspace on this triangle, like different several nodes or degree of freedoms inside each element. The difference of the discontinuous space with probably more familiar continuous space is that if I'm sitting on the edge of the element, the nodes on each side of the edge are independent with each other, so that the global degree freedoms, you can align them with the index of the element rather than the node of the global indexes, so that the degree of freedoms within each element, they stick together within memory, so that once you go over all the nodes in your computation, you go over the memory in a consecutive manner. That's why it's usually better for parallel computing. Yeah. So here is a formulation of the weak form. So you insert, you multiply each side of the governing equation with discontinuous functions, the nodal functions on each side of the equation. You get this weak form, and the weak form you get a volume integral inside the element. So that's a normal integral. You will get it everywhere, even if you're using a continuous method. An additional term here is the numerical flux term. That is a term that accounts for the interaction across elements. So I have said that the nodes across on each side of the edge are independent. So how you account for the interaction of those nodes is through this numerical flux term. It's like a penalty term that you add to make them to link them together. Yeah, and the linear form on the right-hand side accounts for the source in the governing equation. the Dirichlet and Neumann boundary conditions. Yeah, and once you replace these discontinuous functions with a nodal basis, you get a linear system, Ax equals b, and we are going to solve that system with multigrid method. Okay. So in the multigrid solver, you will I get the sense that so you will start with the Finite mesh in your problem. That's the discretization we see before. That's the Ax equals b, and you can use an iterative solver to solve that, like a plain Jacobi iterative solver, a GMRAS. But it usually wouldn't be very efficient because you have different frequency of errors. But your iterative solver usually only tackles a part of the frequencies. So a multigrid solver tries to you use different levels of coarse mesh to agglomerate your nodes together so that you get coarse mesh, and those errors on a fine mesh becomes high frequency errors in the coarse mesh, so that on each level of these multigrid levels, you tackle different frequencies in your error so that you get an efficient system, an efficient solver. And so to be more specific, the multigrid levels I'm selecting here. So first we have a high order discontinuous grid, and then we do a Galerkin projection to make these 10 nodes, 3 nodes in the first level of your coarse grid. And then we will also make it continuous on this grid so that the nodes on the edge are no longer independent on each side of the edge. And after that, we do several algebraic multigrid levels. That's only taking the numbers in your matrix and agglomerate according to the properties of the matrix. And as I said, you want to refine your solution on each level of this grid. And on each level, you do some Jacobian iteration in the most simplistic way. And we usually call those solutions those solving on each of these grid, on each of these levels, a smoother. And the smoother specifically, I'm using a block Jacobian iteration on this Finite level, and point Jacobian on each level after that. And the smoother looks like this. It's like an iterative solver. And the most important thing we need to get to use this smoothing is to get the residual on each level. That is b minus a times x. And how we do that is via the neural network. So we seek a matrix-free implementation. That means we never explicitly form the A here, so we will want to compute each node, each entries in this matrix and save it in the memory, because we usually don't have that large memory in the parallel hardware. We only need to get the multiplication of this A with X. So once we need that, we will use a subroutine to get that. Or here we are using a neural network. It takes in your X and gives you the R. So what does AX consist of? We expand the bilinear form we see before, and so specifically the numerical flux term, it expands like this. So you have the integration of your shape functions inside the element, and this plus here is when you're sitting on the edge. It's on inside this element is the plus side, and the other side, the neighbor of this edge, is the minus side. So you have the multiplication of the shape functions inside the element itself, and the integration of itself and the neighbor side. And how do we actually calculate that integration? We use numerical integration on quadrature points. So if you expand this integration here, you get discrete values of the shape functions, the Jacobian and your solution vector on your discrete nodes and also on quadrature points. So you can multiply those numbers together. And a thing to mention here is that if you want to get the indices or information from the other side of your edge, you will need to gather those information on the other side. That's the gather operation here, the G here. And that's where the graph neural network, the graph plays its role here. So I'm showing a 2D mesh here. It has been discretized into elements. And in a traditional method, you will have a connectivity matrix that tells you which element is linked to which neighbor elements. And essentially, you can abstract that connectivity matrix into a graph. So each element showing as a small triangle here is abstracted into a triangle on this graph. And if they're linked with an edge, so they share an edge, they were linked by an edge on this graph. And you can basically store everything you need for that numerical integration you see on the previous slide on the edge and on the node in this graph. And if you need, once you store them there, you can pass all those informations on through different layers of computation or network layers to get the numerical integration we see before. So I'm giving more concrete examples here using the volume integral. So for example, if you want to multiply the vector field, your vector solution, the guessed x there, it has been rewritten as a u here. If you want to multiply it with a shape function here, you will, first, as I said, you can store all your solution vector continuously in your memory. And because this shape function is the same for each element, it acts as a filter here, as a 1D convolution. So the multiplication of this shape function with your solution vector becomes a convolution operating here. And similarly, you can compute your Jacobian with the multiplication of your shape function with solution with the coordinate of your nodes. And after that, you want to multiply these results together. And for those, you can use other mathematical multiplication or tensor contraction. Those operations provided by PyTorch. And this is how the part of the neural network looks like. So it takes in your solution, the coordinate, and the output would be the numerical integration on quadrature points, summed together to give you the volume integration. And similarly, you can use this procedure for all those integral terms we see before, and get your a times x and give you the residual. So I'm showing some results for the diffusion equation here. So first, we want to test if the integration we do is the same as you would implement it in the traditional way. So we'll test it with a problem with analytical solution so that we can compute the exact L2 norm error so that you know if it's converged in an expected way. So I'm showing two results here. One is in coarse mesh, one is in fine mesh, obtained from the solver, from our solver using neural networks. The analytical solution is like this, is an exponential solution. And on the right, similarly, is another example. So this is just a good picture to show you the results. Yeah, I'm not explaining that. Yeah, so let's see how the accuracy of the solver is. So we're using third order elements. So for this specific integral penalty discontinuous Galerkin method, you would expect fourth order convergence. And as shown in this figure, as you refine the mesh, so mesh size reduced, you get a lower, you get a smaller error, and the reduced rate is further reduced. So it is consistent with the traditional or what you would expect for this specific numerical scheme. And for scalability, we want our multigrid method to scale. That means when your problem size increase, the computational cost also increase. So the number of iteration stays the same, but the degree of freedoms increase, so it will be linear. So in this figure, it shows that as you refine the mesh, and the number of degree of freedoms increase, the number of iterations stays the same. So it means it's scalable. And for efficiency, I use this comparison with a highly optimized solver using the same DG method in the literature to show that our method runs on GPU have achieved a comparable throughput. That's how many degree of freedoms you can process per time. And even though we're not using the best GPU, here, yeah. So that's a method, that's a multigrid method. Next, I'm going to introduce how this is applied to hyper-elasticity, Navier-Stokes, and the free structure interaction. For hyper-elasticity, it has governing equation very similar to the diffusion equation we see before, even the weak form is very similar. The difference is that it's a nonlinear equation, so you have to do some linearization. I'm using Newton linearization here. So at each Newton step, you are solving for the displacement increment by solving this equation here. And to solve this, we apply the multigrid method as a preconditional here. So you multiply this preconditional to both sides of the linearized system, and it gives you a better conditioned linear system. So you get a faster convergence for your linear solver. And again, here are some nice pictures of what we achieved using this solver. So this is a compression of a hollow cylinder under different loading. And for Navier-Stokes, we have a saddle point system after discretization. So for this sum, you can also use a preconditioner multiply to both sides of the equation so that you get a faster convergence in your solver. The specific preconditional we are choosing here is a block triangular matrix. So this MF will be somehow approximate your velocity matrix here, and we are approximate its inverse with one multigrid cycle, the multigrid method I introduced before. And for this pressure Schur complement, we use this preconditioner to approximate its inverse. And again, this the two matrix inversion, one is by direct inverse because it has block structure. The other one, we use the same multigrid method I introduced before. And here are some results. On the left is a comparison of our results with the literature. And on the right, again, I'm showing as you increase the size of your problem, the number of iterations is almost the same, does not increase, even at a higher Reynolds number. Yeah. Some more pictures. And finally, we get to free structure interaction. So we get quite similar equations as before. The difference here is that we use arbitrary Lagrangian invariant frame, so you have to account for the mesh movement here in your advection term. And after discretization, you get a block system, and we are using the preconditioner we introduced before in this triangular preconditioner. And again, for each of these matrix on the diagonal, you can use a multigrid method to approximate its inverse. And here are some results. This is the 3D results of flow in the channel where there's a flexible wall attached to the bottom. Yeah. To draw a conclusion, we developed the graph neural network for the high-order DG method on unstructured mesh, an efficient multigrid method, and we apply it to hyper-elastic incompressible flow and fluid structure interaction problems. And it has been tested on GPU also. I'm sure it's very easy to use this structure on all those hardwares I introduced before. And the next step would be, one thing I'm very interested in is to explore its automatic differentiation functionality for inverse problems.